and then we move on to our second talk. So our second speaker is Jacques-Henri Jourdan. He worked on the Crusoe tool together with Xavier. And so they're exploring a different approach to verifying safe Rust programs by focusing mostly on the values that a Rust program manipulates rather than the underlying separation logic structure, which has kind of very different trade-offs compared to what Prousty does. So yeah, please go ahead.
Okay, can you hear me? Do you see my slides?
I can hear you, but the screen is black.
Okay.
That's your screen is black, so it's probably showing a different desktop.
No, my screen is definitely not black. So let's try something.
Could it be permission error? Maybe you on like Mac and it has some like doesn't allow a program to render or something.
So how about now? Still black?
Yeah, still black.
Okay, let's try this. And now it's still black?
Yep.
Oh.
If you change the settings, try maybe stopping the share and sharing again, because it could be that Zoom doesn't pick up if there are changes. Now it's visible.
Yes, great.
Now it's visible?
Yeah.
Yes.
Okay, well, let's continue like this.
No.
No, it's
So now we see only a small portion of the slide, kind of the rightmost part, and most is black again.
It seems that you have something that covers the slides, and Zoom doesn't allow it to be shareable.
I have nothing that covers the slides. So
What's your presentation? Is it a PDF or?
yeah, it's
yeah, can you mail it to Peter? Maybe Peter can display it.
Sure, I can try. But it seems we've lost him completely. No.
So do you see something now?
We see bits and pieces.
Bits and
They're
pieces.
moving
That
around.
doesn't make any sense, right?
No, it doesn't make any sense.
Can I stop sharing? Pause share? Resume share? No, stop share. And now, do you see something?
It's all black.
It's all black. You know what? I'm going to try to not use the Zoom app.
That's maybe a radical way of fixing the problem.
While we're waiting for Jacques-Henri, we can continue your discussion.
Yeah.
Yeah, I can try getting the Viper example. Let me see.
He's coming back. Okay, so now we see your slide.
Works. So you can hear me,
Yeah.
right?
Almost perfect. Cool.
And you see,
So,
cool. Okay, so the error was to use the actual Zoom app, since the web app was working. Okay, so
cool. Please go
Crusoe.
ahead.
And Crusoe is another tool for verifying Rust programs. Why is Crusoe here? So Crusoe is here because program verification is hard. You know that. That's why you are all in the Newton Institute currently. My take on this problem is that we should use the right tools. And in particular, the choice of a good programming language is important for verifying programs. And choosing a programming language is often a matter of doing some compromises. And in particular, the verification of low-level software is particularly difficult. And the reason for this is that low-level software requires a lot of control about several things. It requires control over the memory layouts. It requires control over the way the memory is allocated and deallocated. And it also requires to have some control about what computation is done and when this computation is done. The problem now is that a lot of good verification languages and actually most of the programming languages don't offer this control, and we're stuck with bad programming languages and bad verification tools for these bad programming languages. And one of the problems that we have is the problem of aliasing. And so the problem of aliasing, I guess most of you know this problem, and this problem comes from the use of pointers, which are privative in low-level software. So if you want to verify low-level software, you will have to deal with pointers, and when you have to deal with pointers, you have to deal with aliasing. So for example, let's take this piece of code. So do you see my mouse or not?
Yeah.
Yeah. Okay. So you see this piece of code. This piece of code is a function, so array copy, that copies an array, a source array, to a destination array. So it takes three parameters: the pointer to a source array, a pointer to a destination array, and the length of the section of the array that needs to be copied. Well, basically, what this function does is a loop, and it copies the source array to the destination array. So what spec do we want to put for this function? Well, basically, we want to ensure, as a postcondition of this specification, that the content of the destination array after the execution of the function, the content of this destination array should basically be the initial content of the source array. And moreover, the function should not modify the content of the source array. So this is the two postconditions that we want to have for this function. Well, however, this doesn't actually work, and this specification is wrong. And the reason for this is that we need the source and the destination buffers to be disjoint. Typically, different tools use a different way to specify this assertion, but basically, you most often need to write this assertion in some way or another. And the thing which is very frustrating is that these assertions are typically trivial. Essentially, you are going to say that everything is disjoint, right? Everything in your program is disjoint. So they typically don't say much, and they're very tedious to write and to prove. And moreover, because they're very tedious and they're very large, they are usually badly handled by automatic provers. So this really goes in the way to proving programs that use pointers. And well, one solution to this problem is the Rust programming language. So it's a language which has been so Vito has already spoke about it in the previous talk, but basically it's a language that has been developed by Mozilla quite a few years ago, and it's been designed for rewriting some parts of the Firefox web browser. So it's high performance, and it gives a high level of control, but with very good abstraction mechanisms. So this seems to be a good way to verify low-level code because it gives you some low-level control over the program. It also gives you good abstraction mechanisms that are very important for verification. And our claim is that Rust is well suited for low-level software. And why so? First, it has a rich type system. So the type system gives safety guarantees. So you will not need, if you want to prove a Rust program, you will not need to prove safety because it's already provided by the type safety. Moreover, it provides non-aliasing guarantees. So this means, so we will see how, but basically this means that we won't need to prove anything about aliasing of pointers. And it also has a powerful abstraction mechanism, which are called type traits. So type traits are kind of type classes borrowed from the Haskell programming language, and it provides you abstraction and genericity. And it's good for verification because then it's going to give you a way to abstract over specification and write reusable specifications. Moreover, another good thing about Rust is that it has a rich ecosystem with a lot of tools and APIs on which we can build verification software. So we can write software that we are going to reuse the existing pieces of software for the front end of Rust, for example. And so the verification tool is going to be easier to write as for, I don't know, for example, a C++ verification tool. And so Rust, my claim is that Rust is a good target for verification, and our tool that we are using for this claim is Crusoe. So Crusoe is a verification tool for Rust programs. So basically, well, the user annotates Rust with specifications. So we have our own specific language, which we call Perlite. And then Crusoe, the tool, translates these annotated Rust programs into a functional language, which is called YAML. And then the Y3 tool, which already exists for quite a few years ago, reads these YAML programs and generates proof obligations that it gives to automated provers to automate the proof. So Crusoe supports plenty of features of Rust, including generics. So it supports polymorphism, it supports type traits, as I said, supports closures, and plenty of other important features of Rust. And the secrets, which we use behind Crusoe, so it's really something very important in Crusoe, but please don't tell it too much because it's really our trade secret here. And that's Rust is actually a functional programming language. So everyone lied to you because you thought that Rust was a low-level imperative programming language, but it's actually a functional programming language. And I'm going to tell you why. And that's actually something that helps verification very much. So let's start with a simple example. So this example is a function inc, which takes two variables x and y, and returns a pair of two integers. Right? What it does is that it adds y to x, then it does some other stuff. It calls another function, whatever, and it returns the pair xy. And basically, in order to translate this in YML, we are able to translate this apparently imperative program because it's actually incrementing the variable x here. So it seems like it's an imperative program, but we're actually translating it to a purely functional program, which is this inc function. So basically, the idea here is that as long as there is no pointer, mutating a variable like this x variable is like shadowing. And this is valid because we know for sure that this doStuff function is not going to modify this local variable. It's a local variable, so it doesn't have access to it. So how do we do this translation? We give a name to the value of each variable at each program point. And basically, each time we mutate a variable, we use variable shadowing, like here, for when we write let x equal x plus y, to denote mutation. Yeah. And the reason for that, that's variable can only be mutated directly by actually accessing them by their actual name, so we can track their modification just easily like this. No, well, local variables are a good thing, but there is also the kind of other ways of storing data in Rust, of course. We can use pointers and heap allocated memory in Rust. So how do we do this in a purely functional way in Crusoe? So for example, there is these box pointers in Rust. So this is a pointer to a value which is stored in memory, but which we own fully. That is, we are sure that nobody else has a pointer to this piece of memory. So yeah, these pointers are allocated on the heap. And the guarantee that the type system gives us is that there is no alias to these pointers. So now if we have a program that uses these variables, so let's take a variant of the previous program where instead of having integer variables, you have pointers to integer variables. Well, basically we do the same thing in the program, right? And the nice thing that we can actually translate it to the same program. And the reason for this is that because there is no alias, we know that nobody else can modify these variables. So we know that if any variable are mutated, then we are the mutator. So this means essentially that, well, we have actually used the box to allocate memory, but functionally, these variables actually behave just like their contents. We are not actually able to see that we are using a box in the semantic sphere, right? So, and this is actually why we call this box in Rust. It's just a box that contains a value, but we don't see that it's actually a pointer. It's just a way of storing the value. So, well, it's still very easy to translate this program just by translating box pointers to their inner value. Now, well, there is yet another kind of pointers in Rust, which are shared borrows. So a shared borrow in Rust is a kind of temporally immutable pointer. So it's noted like this. So it's $t, and basically it's a pointer to a piece of memory in the heap or in the stack or somewhere. And this piece of memory, we are promised not to modify it through this pointer. So because it's immutable, we are going to use it. We are actually able to use it as if it were their content, just like box, right? So if we have this program, for example, we create a variable x which we initialize to 12. And then we create two immutable borrow to it, right? So by copying it to it, so not only it's immutable, but it's also copyable. So we can actually create copies of it, but that's fine because we know that the content of the variable is never going to change. Then we can call a non-function with this pointer. And finally, we can do some computation with it, right? And again, we are going to be able to translate it as if it was a purely functional program, because we know for sure that the content of the borrows are not going to change. We can just consider that the borrow is actually it functionally behaves just as its contents, right? So to summarize, the reason all this works is that Rust enforces a very important invariant in his type system. And this invariant is that for any piece of memory at any given time, you are either allowed to mutate this piece of memory, or this piece of memory can have several pointers to it, several alias pointers to it, several alias active pointers to it, right? And it's not possible to both be able to mutate a piece of memory and have several pointers to it. And this is what makes our translation valid. This is this crucial invariant of the type system. And the reason why it works is that because this combination is not possible, we cannot have this action at distance, which is the fact that the value behind a pointer can change without accessing the pointer. That is, it's going to change because someone else accessed the value through another pointer. Because of this, it's very easy to track the changes of a variable because there is only one way to change the value of the variable. It's the pointer that we own directly, right? And thanks to this property, we can see a Rust program as a functional program. And the way Crusoe works is actually by translating Rust program into a functional program in YAML. Well, so far so good. So now we think that everything is easy and there is nothing to do. But there is actually one point where things get complicated. The things get complicated when you go through mutable borrows. So mutable borrows are yet another kind of pointers in Rust. And a mutable borrow is a pointer that gives you mutable access to a variable, but only for a temporary duration. So you get a mutable access to a variable. You are sure that there is not going to be any aliasing to this variable. But after some time, which we call the lifetime of the borrow, you will lose the property of this borrow, and someone else, the lender of the variable, is going to get access to it after the end of the lifetime. So let's have an example. Well, the type vext is in Rust. It's a type of extensible arrays. That is arrays that extend automatically each time you add new elements. And so these arrays have a function, the function push, that takes a mutable borrow to a vector and the value. And essentially what it does, it takes the mutable borrow to the vector. So it takes a pointer to the vector. It does whatever to add the value, and then when it's finished, it gives back the ownership of the variable to the caller, so that the caller can use the array again. So that's one function that uses mutable borrows, but there is another pattern which is very common. It's the function index mute, for example, which takes a mutable borrow to a vector, an index, and returns another mutable borrow to the kernel of the vector. And the thing here, which is enforced by the type system, which is important, is that both mutable borrows have the same lifetime. That is, you give a mutable borrow to this vector, which is only valid for some duration of the time, and gives you back an inner pointer to the vector for the same duration of the execution of the program. And once this lifetime will have ended, then you will no longer have access to the inner pointer, and you will get back the ownership of the full vector outside. So this is a very important pattern in the Rust Rust APIs in general. So let's see how do we translate this function in our in Crusoe. So let's take, for example, the example of this function. So we create a vector with two elements, right? So well, that's easy, right? We will create well in YAML we will create a list with two elements. Let's consider that we model vector with list, whatever. Then well, we will call the push function, and then well, we will pass it the vector v, right? But then, well, essentially we will translate it to a call to the push to the push function in the functional translation. But then what happens to the change to the way v changed? Like we call the function, but this is supposed to be a purely functional function, so nothing happens here. And something even weirder happens for the index mute function. So we give it well, so here we give it a borrow to the vector and the index 2, and we ask it to actually increment this element number 2 by 1, and then we give back the ownership of the vector. But then here, while index mute is going to be given the kind of the vector and the index 2, and then it returns the value of the inner elements, then we can add 1. But then how do we say that the new value that we've just computed has to be used to update the vector of v? There's something missing here, right? And the solution to this problem is to use prophecies. So prophecy is a ghost variable that has been used. It's a mechanism that has been used for a long time to prove certain kind of programs. So this is ghosts. So this means that they don't actually exist in the program, but they are very useful for the proof. And they exist for a long time. It's something that's appeared in a paper by Lamport and Abadi in the 80s. The main idea of prophecies is that you will store in a ghost variable a value that's a value about the future of the execution of the program. So it's essentially a ghost variable that you can read before assigning it. So you are able to first read the variable and then assign to it. So a typical proof that uses prophecy variable is in 3 steps. So first, you create a prophecy variable very early in the execution of the program, and then here, when you create the variable, the prophecy gets a value. You don't have any information about it, but it gets a value. Then you can use this value in the proof, and you can actually do a proof which depends on this actual value. And then at some point, you will decide that you will resolve the value. So you will actually assign a value to the prophecy. And at that point, you will learn that the value of the prophecy, the value that you've been used since the beginning of the proof, is actually equal to the value you've just assigned to the prophecy. So this is a kind of weird way of thinking about the program, but it's very useful, in particular in the context of Crusoe. And we use it by translating any immutable row by pair of first the current value that we denote as star x, which is the current value of the mutable row, which is something that we already have in intuition. It's the same notion for box, for example. And the second component of the pair is a prophecy on the final value of the borrow. So it's something that we guessed about the value that the borrow will have when its lifetime will end. And so we create this prophecy when you create the mutable borrow, and we will use the prophecy to assign the new value of the variable that we borrow. So let's take an example. So for example, the function push that we've seen before, the specification for this function is going to be the specification that I've just put here. So essentially, we're going to say as a postcondition that the prophecy of the vector, so the final value of the borrow, is going to be equal to the initial value of the borrow appended with the new element. So let's take an example of program that uses this specification. So first we create the vector. Well, when we translate it, it's the same thing. We create a list, right? Then we create the borrow over the vector. Well, basically we create a pair of the current value of the vector and of a prophecy that we use any value, a non-deterministic value that we create here. And then we call the push function with this bor, which is a pair of the current value and the prophecy. Well, this needs to be fixed here. It's a 2. And then, we are going to assign to v when the lifetime of the bor ends, that is after the call to push. We are going to assign as a new value of v the prophecy that we've created for the bor. So now after the call to push, we know that the prophecy of the bor, it's SND here, it's not FST, right? The prophecy of the bor is equal to the value of v appended with the integers that the element that we've added to the vector. So when after this new assignment to v, we will be able to learn that v is actually equal to the list 1, 2, 3, just as we expect. So in practice, this assignment, we place it at the place of creation of the bor, so that we don't have to do any analysis, and because we are sure that nobody else is able to access the vector, it's the same thing to do this assignment here or to do it here. So let's take another example, the example of index mute. Yeah.
I think you already told me once, but I would like to hear it again. Yeah. Why didn't you have multiple value returns on the function so that the borrowed value is returned and read back into the borrower's value?
So this is so it's a bit sad because this is essentially what Sean does in our Iris. Well, essentially, we initially planned to have a third speaker in this workshop about the third tool, which does something like this. The problem with this approach, and the reason why we don't want to do this approach, is that essentially this is going to change a lot the type of the functions, and in particular, it's not clear how you would do the translation if, for example, you have data structures that contains bors. What if, for example, you have a function that takes a list of bors? Then you will have to return several values about each element of the list, and at some point you will have to have a postcondition saying that the list has the same length or something like this. It seems very artificial, and it needs to be done automatically, and it's not clear at all how you would do this automatically. And in particular, it's not clear how you would do this without breaking the abstraction barriers of the various data structures that would contain bors.
Let's show up similarly in your translation, where now you would have a list of pairs.
I'm sorry, I don't get the end of the sentence.
Sure. So doesn't it show up in the translation now that you have here, where if you have v bor equals v comma v prof, so you have a list of these pairs there, right? In the translation, if you had a list of borrowers.
I'm sorry, but I really have trouble hearing what we say.
You move closer and see if that works. Can you hear me?
Yeah, vaguely, yeah.
Okay, but I mean, if you had a list of borrowers, wouldn't that also show up as a list of pairs in your translation?
Yes. So if you have a list of borrows, then we would essentially have a list of pairs. Yes. If you have a vector of borrows, then you would have a sequence of pairs in our translation. So essentially, it's a very structural way of translating types. Essentially, you translate borrows of T to a pair of translation of T's. It's very structural. It's very and because this translation is very structural, we are sure that it's very composable, and we don't have any. Well, we don't think we have any problem with composability with this approach. So yeah, let's take another example, for example. And this other example makes, I think it makes your proposal even more subtle. I'm not saying it's not possible, because that's essentially what Sean is doing. I'm just saying that things get even more complicated. So index mute. So again, index mute takes a bore of a vector, an index to this vector, and returns a bore of one element of this vector, and this is the element at the index passes parameter. Then, what are the post conditions of this function? Well, basically, first it ensures that the current value of the results is equal to the element at index idx of the input vector. So this is basically what you would expect. And I mean, any specification of this function that doesn't have this would be really weird. The thing which is interesting is that it also works for prophecies. So the prophecy for you get as a post condition that the prophecy for V contains at index idx, it contains the prophecy of the returns value. That is, when the returns bore will end, we will know this final value, and this knowledge of the final value will go back to the kernel of the vector V. So thanks to this, you will learn how the vector V has been updated through the updates of the return bore. And then there's the third post condition that says that's essentially the current value of any index which is not the index passed as parameter is the same as the prophesized value. So essentially, this means that all the borrows to all the other elements will not change. Nobody has access to it until the end of the borrow. So we know that it does going to change. So we know that their final value right now. So how any program that uses this function is going to work. So let's consider this program that takes a vector of 3 elements, 1, 2, 2. Then it creates a borrow to this vector. It calls the function vBor, and then it calls the index mute function to the borrow to the vector, and then it actually increments the return borrow, and finally it returns the value. So what's happening here when we translate it? So first we are going to create this lists, right? Then we create a pair of the current value of the vector and the final value of the borrow, which is the prophecy. And then we assign to V the prophesized value of the borrow, so that we know that once all this is going to be finished, the value of the vector is going to be the value that we prophesize now for the vector. Then we are going to call the index mute function as before. And while we do the incrementation, so we only increment the current value, the prophesized value doesn't change. It's a prophecy about the final value. It's not, it cannot change. And then, well, at this point, we know that X is no longer going to be used, so we can resolve it. So essentially, we know it's not going to be used, so we know that it's not going to change either. So we know that its prophecy is going to be equal to its current value. And this is why we can resolve it, that is, assuming that the two values are equal. So then now, in the proof for Y3, what's happening is when we call index mute, you will learn that the first component of X is going to be equal to 2. Well, just because the element at index 2 of this vector is 2. And we know that the vector V is going to be equal to 1 to second of X, which is the prophecy. This is essentially what says the 3 post conditions of the index mute function. Then, once you will call the assume function, you will learn that the first component of X, which is 3, is going to be equal to the second component of x, which is v of 2. So you will essentially learn that v equals 1, 2, 3, which is what we want. So let's take this function as a last example. So it's a function that takes two borrows to integers, and it returns either the first one or the second one, depending on which of them is the larger. So which spec you would give it? You would give to this function? Do you have any idea? Okay, no answer. No worries. The spec that we want should allow to prove this fact. Essentially, it gives you would have a function that takes two integers as parameter in boxes, but anyway, then you return the borrow to the larger one. You increment by 7 this value, and then you will have to be able to prove that the difference of the two value is larger than 7, whatever the initial values are. And well, the specification that is allowed to prove this in Creusot is the following one. It's quite simple. It doesn't say anything about ownership or anything. It's just saying this. And what it says exactly is that, well, there's two different cases depending on which of the two borrows are larger. If A is larger than B, then well, if A larger than B, then we are allowed to resolve B. We know that no changes are going to happen to B, and the borrow which is going to be returned is A. So it has the same first component and second component. And conversely, if A is larger than is smaller than B, and if we give Max-Mute this specification, then after the translation, Y3 is able to prove the test function automatically without any help or anything. So I think it's a good example to see that this translation is very powerful. Well, so I told to you a lot about Creusot and about how it works and about these prophecies and how it's wonderful. But now the question is it actually sound? And it's actually a very subtle question. And the reason why it's very subtle is that prophecies. With prophecies, you can create causality circles. So if you use a prophecy to change the behavior of a program, so that you use prophecy to change the value you are going to resolve the prophecy with, then you're creating a causality circle and potentially an unsoundness. So to resolve this problem of causality circles, we rely on type system guarantees. And this is quite subtle. So we have a proof of soundness of this mechanism. So basically, this proof of soundness builds a logical relation on the type system of Russ. It uses the Harris separation logic, and it's fully mechanized in Coq. And it's essentially an extension of the Rosberg proofs that Ralph Jung already talked about in a previous talk, I think, last week. But yeah, I won't talk about this much more than this. But yeah, it's sound and it's subtle. So now let's take a more subtle and more not subtle, a more advanced example of using Creusot for proving a program. So let's take this function of a GNOME sort. So a GNOME sort, it's a sorting algorithm, which I like very much because it's a sorting algorithm that uses only one loop and one test. So it's very simple sorting algorithm. It's quadratic, so it's not completely inefficient, and it's also quite easy to prove, in particular in Creusot. What's a GNOME sort? So it's a function that takes a mutable borrow to a vector as a parameter, and then it uses a loop with an index I that is initially set to 0, And while I is smaller than V, if V of I minus 1 is smaller than V of I, then well, they are well ordered, so we increment I. Else, we swap the elements at position I and I minus 1, and we decrement I. That's all we need to do to sort an array. And the invariant, of course, is that V is sorted between the index 0 and I, and that's, well, V stays a permutation of the initial value of V. So in Creusot, in order to do this, we are going to use prophecies for specifications. So essentially, we're going to say that the final value of V is going to be sorted. We are going to say that the permutation, that the final value of V is a permutation of the initial value of V. And as an invariant, we are going to say that V is sorted between 0 and I, and that V stays a permutation. We are going to use logic predicates that we support in Creusot. So you can write in a Rust syntax logic predicate that we define somewhere else. And this function is generic over any type T which is implemented the ORD trait. So the ORD trait in Rust is a trait for an order relation. And so this poses the question of how do we actually specify this ORD trait? So ORD is a type trait, so it's a type class. So it defines some operation that's on a type. So in Rust, the definition of ORD is more or less a function TMP that is returning an ordering for 2 elements. Well, there are other functions, but the most important one is this one. So in Creusot, we extend it with a logical function, CMP log, which is a purely logical function, which is also returning an ordering given 2 elements. And we ask to prove some properties about this logical function. That is, well, basically it's another relation, so it's transitive and reflexive and antisymmetric. Well, and then as a postcondition of CMP, we say that it has to return a result equal to the logical function here. So we have 2 different kind of functions. We have logical function and program function in Creusot. And I think that's a very powerful pattern to specify generic function in Creusot. And that's something that we use for many different traits, for defining the behavior of traits. So I'm going to go towards the conclusion because I don't think I have much more time. So the current status of Creusot is that it supports many challenging features of Rust, which not all of the different version tools for Rust supports or supported, or more. Anyway, it's required quite a bit of work, and I think it's important because there are features which are used in quite a few programs in Rust. So it supports borrows in loops with borrowing, so very advanced borrowing patterns. And the way we support it is basically we don't have to do anything to support them, just because we don't track ownership. We ask Rust to track ownership, and then we have this functional translation to YML, which requires that ownership has been handled, but which doesn't reason about ownership at all itself. It also supports recursive data structures, and in particular, it supports storing mutable rows in data structures. It supports higher order functions. It supports closures, and even closures that actually mutate their environments. That's something that we support, that we are able to do. It's not particularly easy to specify, but that's something that we can do. It supports polymorphism, in particular polymorphism constraints by traits, just as in our GNOME sort function. It supports intermutability, that is breaking this general rule of mutation XOR aliasing. So in Rust, you can actually break this rule in a very directed way. So there are some types in the standard libraries that lets you break this rule, but without making the rest of the type system unsound. And these are, well, types that require some challenge to support in our verification tool, and we are able to support this. And more importantly, Crusoe has been used to prove some non-trivial programs. So for example, it has been used to prove crossats. So crossat is a CDC sat solver, which has been implemented and proved correct by Sarek Kotam. I hope I pronounced his name correctly. So Sarek is a Norwegian master student, and he has been able to prove it. So he downloaded Crusoe and he learned how to do this, and he has been able to prove correct crossats during his master studies. So Crusoe is not something which is very difficult to actually learn and use even for a student. And well, crossat is actually a good software because it's competitive with other verified site solver which exists in the wild, which is very impressive for master thesis. So to conclude, there's plenty of other work to do on Crusoe. So the subject of Xavier's internship, which he's doing currently at SRI, is to prove a toy SMT solver. Well, essentially you can see it as a continuation of the SAT solver project, but it's a completely different project actually. Another direction for future work is to support Gauss code and Gauss resources and type invariants. So we have a very basic support for Gauss variables, but it's not very mature and needs a lot of work. We would like to specify and use Rust iterators. So this is something we have a lot of ideas to do about. We need to implement these ideas and to see whether it actually works in practice in code and whether we're actually able to provide concise proofs of code that use iterators. And then, well, we have many other ideas, and perhaps if you want to work with us, you will bring some new ideas to do, stuff to do with Crusoe. So thanks for your attention. I would be happy to take your questions. You can go to our GitHub repo to see our code and examples and so on and so forth.
Great, thank you very much. Questions, please.
I do have maybe a naive question. You can hear me?
Yes.
Yeah.
So you started with some.
I am the only one, but not
No,
hear anything.
I think the whole room just disconnected.
My question is, I mean, in some sense, this translated code looks simpler than the original Rust code.
Yes.
So why not just use this functional language rather than Rust?
Well, because so that's a good question. When we are interested about functional correctness.
Yeah, just give me a second. Yeah.
Maybe it's post time.
So can I speak now?
Now it's fine. Yeah.
Okay.
So I grew up with ML. I love ML. That I could appreciate your translated version. That was clear to me. And you started with something that I didn't understand, and you were understanding your initial Rust language by the translation. So
I think the question is Rust just a painful way to write a functional program?
Yeah. Because because after all, it's functional. That was your opening statement.
So, well, I mean, I come from the ML community, so you are not going to convince me that you can write concise programming in functional programming languages. The thing is, our translation is a logical.
All these examples that you throw at us, you were explaining their sound using a translation.
Right? So the thing, so there are several points here.
Yeah.
First, it's a logical translation that we use only to prove functional correctness. So we when we do this translation, we can actually forget everything which is about memory representation or the way the code is going to be executed on the machine, the way the data structures are going to be represented in the memory, because this is not the point of functional verification.
So you say the
but
operational
this is-
semantic of the translation is different. They're different in an operational semantic view. Is that a way of saying? So what is saying that this translation correct? What is
Say, I think you're saying that the Rust memory layout may not match that of the functional translation.
yeah, that's what.
Yeah, exactly. So the memory layout of the translated program doesn't match the memory layout of the initial program. And the thing is, for what we call functional correctness, this is not something we are interested in. This is something which is interesting for Rust programmers because they like to have the control over this and they like to choose the way data structures are represented in memory because of performance issues. But when you actually want to prove your program, you are not interested in this. So this is one point. Then there is another point. It's that our translated programs are not actually executable. They're not executable first because of these prophecies. Right, when you create a prophecy, you're actually guessing what's going to happen in the program in the future, and this is of course something that you can execute. And for example, and the typical typical example of this, the typical example of this is mutable borrows, right? You don't have mutable borrows in ML, and this is something which is actually very much useful when you are actually writing Rust programs. So, well, I don't know whether I answered your question.
No, you just did a fair job. Thank you.
Okay. Any other questions? So maybe in the meantime, could you say a few more words about how you handle interior immutability? Do you introduce some kind of annotation on immutable references, which ones might be used to change data structures?
Yeah. So so for now we have a quite a basic support for intermutability. The way we support intermutability, well, the way we support SAL essentially, because it's the only intermutable type which we actually have. We actually have examples that is working for it. Is that we associate any cell with an invariance for the values that it can contain. Well, when you write a value to the cell, you have to prove that the invariant is verified. And when you read a value from a cell, the only thing you know about this value is that it verifies the invariance.
But so let me see whether I understand this. So if you build a data structure on top of cell, so you don't recognize by looking at the type name that it uses a cell internally, then the usual framing story is not sound anymore, right? Because you can no longer rely on the fact that an immutable reference will not be used for mutations because it might be internally by changing the cell.
But with a cell in Rust, you cannot have a mutable borrow in a cell. It's not something which is allowed.
Okay.
So that this is something which is quite subtle with intermutability. It's types which allow to do both mutation and aliasing, but it doesn't break the mutation XOR invariance, XOR aliasing property, in the sense that you cannot create alias mutable borrows, for example. So, for example, for cell, you get a get and a set function that lets you read and write the cell, but it doesn't give you a pointer to the content of the cell.
Yeah, but I meant something different. Imagine I implement my own tuple data structure, and the tuple consists of two cells. Okay. So now if I use the tuple and I have an immutable reference to a tuple, I should not assume that passing this immutable reference to another method leaves the tuple unchanged, because that immutable reference could be used to obtain an immutable reference to the underlying cell, and then I can use interior mutability to change the value of the tuple after all.
Well, but the value of the tuple that you observe is not the value contained in the cell. In the model, in the translation, the value of the cell is just its invariance.
I see. Okay, so those invariants kind of percolate up the type hierarchy. Yeah. I see. Okay, that makes sense.
So you never actually you cannot, in the specifications, for example, you can never say the content of the cell is that value. Mm-hmm. You can always say the content of the cell is an invariant that is that invariance, or
right.
All
right, good. Thank you. Any other questions? Well, if not, then let's thank both speakers of today's afternoon session. So I think these were two really interesting talks. And so now everybody has a bit of an overview of what Rust verification is all about. So thank you very much. Shankar, any final words?
Thank you very much, Peter.
Yeah, I'd like to thank the speakers and organizers for putting together a very nice program in such short notes. This is a really important topic. I think the talks that you're given here are going to be things that we discuss, not only in the rest of this verified software program, but well into the future. This is a really central topic for us. Thank you.
Thank you.
Okay, cool. So then let's close the session for this afternoon, and hope to see you all very soon.
Okay.
Bye-bye.
Bye. Bye. So, yeah.